Hey everyone, in this tutorial I'll be showing you how to model a green roof in Causeway Flow. Now before we begin, I would like to thank all the YouTube members that have joined the channel. This means a lot to me because it's what's encouraging me to keep making videos even the views are not that high. So thank you for keeping me making videos. Now modeling a green roof in Causeway Flow, in my opinion, you shouldn't bother too much with it. And it's not just only me saying this, it's actually the Serial Suds manual as well. So you can see here in the peak flow design 12.43 section, the reduction in the volume of runoff from a green roof for an extreme event is unlikely to impact the downstream attenuation storage requirements. Critical duration events for development served by SUDs are commonly of the order 12 to 36 hours, which tend to be representative of autumn and winter conditions. Now, even the Serial Suds manual says the green roof won't impact the attenuation so much, but there are cases that we actually need to model green roofs. But I would question you and play the devil's advocate, why green roof and not go for a blue roof? Blue roof have more storage, they can be treated more as a geocellular at the roof basically, and basically they have more attenuation. But for this tutorial, we're going to focus on how to model a green roof in Flow, and the blue roof we'll keep a separate tutorial. So subscribe so you can stay tuned. Before we begin, I want to share the results of modeling a 200 square meters green roof, a network with the green roof and a network without. Honestly, the difference is only 0.3 meters cube in reduction of flooding. In some sites, that might be a winner, because you don't have any extra storage because of site constraints. In some others, maybe you could oversize a manhole or a pipe to mitigate that. But overall, I would not encourage to model green roofs, or let me rephrase it. I wouldn't worry too much about modeling your green roof for the following reasons. A, if we go back to a Serial Suds manual, the evapotranspiration rate during summer is 3 millimeters per day. But during winter is 0 millimeters per day. That's all and good. But that leads to a question. Does that mean that I will have to run a network only for summer at 3 millimeters if I modeled my green roof and then remodel it for winter? Wouldn't it be more ideal just to take the worst case scenario? That means 0 millimeters evapotranspiration per day. So I would encourage always to model the worst case scenario, because what's the point of modeling a green roof, run it for summer for 3 millimeters when it's going to be 0 millimeters per day? It will not have any impact. So you start seeing how slowly it doesn't make any sense to model for summer. You need to model the worst case scenario, right? To see and make sure your system works. Now, the other reason that green roofs are slightly useless in the winter period is because that in summer, the green roofs are dry, therefore they can attenuate some volume. So I created this 3D model in Blender. It's a free software that you can dabble with 3D modeling. And therefore you can attenuate before you discharge, for example. But in winter, usually the green roof will already be saturated. Therefore, when it rains on the green roof, it will just straight go out because it's already filled up, it's already wet. So therefore, I wouldn't bother modeling the green roof for the summer, like make it dry and just calculate the time of entry or play with the decay coefficient just to see how fast we'll leave the green roof, etc. When the worst case scenario, which is winter, it will just leave the green roof straight away. So enough with all this theory. Let's go to how we model a green roof. So step 1, put your green roof node. In my case, I will create a node. I will add the cover level to the roof level, and that is a practice I do because the blue roof will also be at the cover level and the node represents the downpipe. Then I would draw the catchment area that will go through the green roof. I'm not drawing the green roof area, I'm drawing the catchment area that will go through the green roof. It might be the same, it might be slightly bigger, but it won't be less for sure. So we've got a 200 square meters of catchment that will go through the green roof node. Then we are going to go to our hydrographs. We're going to insert in the node column our green roof node. Then we have two options. You can do design modifier or time area diagram. I propose to stick with design modifier, and then what we're going to do is add the depression storage area, which represents the area of the green roof. So in our case, it's going to be the same. So 200 square meters. Now the depression storage depth, usually it's 5% of the green roof thickness. So if your green roof is 150 mil times 5%, that is 7.5. So I'm going to be more conservative here, and I'm going to go for 7. Evapotranspiration, I'm going to go with the worst case scenario, which is 0. Now you can see you can have actually selected storms, but I want to run for all of them. Now the override design area, that means that whatever area I was putting in that catchment, it will be overrided by the area that I put in the depression storage. Same with the design additional inflow. But in our case, I'm not doing that. All I'm doing is basically specifying the green roof so it can get some storage and the 0. If you want to go with the method of the time area diagram, basically you need to take into account the decay coefficient. So basically, I don't believe there are any clear guidance on the time of entry or like the time it takes for water to filter through a green roof. But as I said, because in winter it will be saturated, it will pretty much exit straight away. As soon as it rains, it will exit. If you want to dabble with that, I would suggest you just do a time area diagram and then just amend it accordingly. For the blue roof, we will play with the time area diagram, but not in this video. So let's go back to design modifiers. That's our green roof, and we're just going to run the simulation. Wait, let me check if I've ticked it. So let's tick that. And that is the one without the green roof. So let's run both. So if we go to our results, you can see that for the 100-year, we've got 1.735. That's because it's not similar with the results here, because I increased slightly the depression storage depth. And then in the without the green roof, it should be 2.3, I would say. Yeah, it's still 2.3. So you can see it has very minimal benefit to the overall scheme. So what would it look like if I actually put evapotranspiration of 3? So let's do evapotranspiration of 3 and let's run it. So it was 1.7 flooding. So let's see if that will be any less. So it's still 1.7. So it's not much of a difference, to be honest, because it's millimeters per day. So overall, what I would like you to take from this video is don't worry too much about modeling your green roof. And if you still want to model it, this is how you do it. You just put a hydrograph, you put your depression storage area, your depression depth, and evapotranspiration of 0, because this is in accordance with the Syria Guides Manual. It is in section, I'll tell you now, 12.4.4 volume control design, where it says the rate of evapotranspiration is often assumed 3 millimeters per day in summer and 0 millimeters per day in midwinter. And yeah, I hope you found this tutorial useful, and I'll see you in the next one. Thank you.